In lab number 4, what we are going to do is we are going to study the resistivity of a resistance and the relationship between the resistance of the resistor with the length and the area. So we'll go into lab handout and we'll see what we are going to do. So there are two parts in this lab. The first part, we are checking how does the length is going to affect on the resistance. In the second part, we are going to check how does the area of a wire going to affect on the resistance. As we know that we do know that resistance can be given by resistivity rho length over area, cross-sectional area. Now, if we increase the length, resistance is going to increase. If we increase area, resistance is going to decrease. That is the relationship. So for in our first part, what we are going to do is R stands for resistance, rho stands for resistivity, L stands for length, A stands for area. We are going to keep resistivity at 0.50 ohms per meter, and area we are going to fix closer to 7.50. If you cannot get into exactly 7.50, whatever closer to 7.50, make sure to record it in here. Let's say for ours 7.50 square centimeters and resistivity is 0.50. Make sure to record it in your table. Now, you can access your simulation just like for the other labs by clicking on this link, or you can copy and paste this URL to your web browser and you can access your simulation. In the simulation, you will have, this is exactly how the simulation gonna look like. You will have three bars. One will allow you to change the resistivity. One will allow you to change the length. The other one will allow you to change the area. And by holding this button and dragging it up and down will allow you to change whatever the number that you want to change it. So for ours, we had to fix rho, which is the resistivity, into 0.50. At the very beginning, when you open the simulation, it should be at the midpoint. That is the midpoint. So you might not have to change it. And the area, which is at the midpoint, which is 7.5 square centimeters. So keep them as it is. Only thing that you're going to change is resistance, the length of the resistance. You can drag it up or drag it down to change the resistance length. When you change this, you will see that this number is also gonna change. This is your R. So in your table, you have to mention what is the resistivity that you fixed, what is the cross-sectional area that you fixed, and then we are going to change the length, and we are going to observe the resistance, and we are going to fill the whole table. Let's go to the simulation. So when we go to the simulation, you will see that this screen will pop up. So you can see that it's already, the resistivity is at 0.5, so you don't need to change it. The area is at the midpoint, which is 7.50 square centimeter. You don't have to change it. Right now, you can see that the resistance is 0.1364, 2.04 centimeters. Now, when you go into this bar and hold your left mouse button and drag up and down, that will change the length. And you can see that the resistance also changing right up here. So your first reading should be closer to 2 centimeters. So make sure to have if you cannot get into exactly 2 centimeter, go as much as closer to 2 centimeter. For me, I can go until it get to maybe 2.04. So that is the smallest number that I can get. That is my L. This is my R, 0.136. Now we have to go back to the lab handout and record it. 0.136 resistance to 2.04 centimeters. Let's go back to the resistance. So my length was 2.04. My resistance was 136. My resistivity was 0.5. Cross-sectional area was 7.50. And then you can change your length again and record it. Let's go back again. Again, I can change my the length into maybe 2 centimeters, more 2 centimeters, 4.02 centimeters. The corresponding resistance is 0.268. So I'm going to record it back again. 0.268. 0.268, and the length was 4.02 centimeters. Now you're going to select any distance that any length you want and record the corresponding resistance. Once you fill the whole table, then what you're going to do is you're going to draw a graph. Resistance, that means this column in y-axis R, and length in x-axis, this column in x-axis. Then you should be able to fix a linear graph and get the slope of the graph. You need the equation on the line. You can see that the slope of the graph from our equation is going to be slope of the graph equal resistivity divided by area. Therefore, we can calculate the resistivity from the graph if we know the slope. Slope time area is the resistivity. So area is already here. Slope, you can get it from the graph and calculate the resistivity. Now, once you have the resistivity, make sure to have your values in the proper numbers. Once you calculate the resistivity, that is your experimental value. This is the actual resistivity. This is the theoretical resistivity. So you can calculate the present error, the absolute value of experimental resistivity minus the theoretical resistivity, divide by theoretical resistivity. The theoretical resistivity is this. Experimental resistivity is the one that you just calculated from the slope. Then find out the present error. In the second part of the lab, what we are using is the same equation. However, we are going to change what we are going to change. You are going to keep the resistivity as constant and the length of the wire as constant as well. Now what we are going to do is, keeping the length as a constant, we are going to change the area, and we are going to see how does the area is going to change the resistance. So if we go to the simulation, you can see that we have to fix our resistivity to 0.5 and length to 10 centimeter. And then we can change the area starting from around closer to 2 square centimeter, and then you can change it. So we'll go to the simulation. Okay, so we are going to keep the resistivity at 0.5, length as 10 centimeter, go closer to 10 centimeter. You can reset it to get, yes, if you reset it, it will go into the 0.5 centimeter resistivity and length 10 centimeter. Now you can change the area. We'll go closer to 2. So this is how close I can go into 2 square centimeter. You can see that my resistance is 2.46. So I'm going to go and record this. 2.46. Two point 2.46. Oh, that is the resistance. 2.46 resistance. The area was 2.0. It says 02 square centimeter. And you can select the other values as well for different areas, collect different resistance. But in here, you can see that the third column asks you to figure out what is 1 over area. So when you calculate 1 over area, you have to get 1 over, for our first data set, 2.02. So my 1 over area will be 1 divided by 2.02 is going to be 0.495. So you're going to do, once you figure out the area and the resistance, you have to calculate the 1 over area. The reason for that is, if you look at the equation, you can see that resistance equal resistivity times length divided by area. So if we are drawing a graph resistance versus area, the actual relationship is 1 over area. So we are going to draw a graph resistance versus 1 over area. Once you draw the graph, you will see that the slope will be equal to resistivity times length. So you are going to draw a graph. Resistance are in the y-axis, this value, and 1 over area, this value in the x-axis, again you're going to get a straight line. So the slope of the graph will be equal to resistivity times area. Resistivity times the length that you mention here. Out from the slope, you can check that you can calculate the resistivity will be equal to slope of the graph divided by length. So again, you're going to calculate the resistivity from the graph. This is your experimental value for the resistivity. This, whatever you record here, which is 0.5, is the theoretical resistivity. By using theoretical resistivity and the experimental resistivity, you can figure out the present error. Present error will be absolute value of experimental resistivity minus theoretical resistivity divided by theoretical resistivity times 100. So those are the two things that you have to do in lab number 4. You have to have two graphs attached. By using the two graphs, the slopes of two graphs, you're going to find out the resistivity twice. The first one we did with changing length by keeping the area constant. In the second part, we changed the area by keeping the length constant. And each time you have to calculate the present error for each case.